assessment is on from page 172, the notes. So it's a sample, but not of everything. I mean, your assessment will have similarities, but also some fairly significant differences. It's just there to give you an idea of the layout and the length. But like say this first question, something like this mightn't be on it, and something that isn't on it on this one might be on your one. So really everything is examinable. Okay, so the first four terms of the Maclaurin series. So our Maclaurin series formula looks, certainly the first four terms says it's y of 0 plus y dashed of 0 times x plus the second derivative of the function divided by 2 times x squared plus the third derivative of the function at 0 divided by 3 factorial, which is 6 divided by x cubed. So it's a way to approximate this thing. So we just have to calculate some derivatives and evaluate them at 0. So we're talking, first of all, y of 0 is log of 1 plus 0. And this is log of 1, which is equal to 0. That's the first one. Now, to differentiate this, strictly speaking, if you kind of forget about the chain rule, you're okay, but we'll still do it that way. So we're differentiating log of 1 plus x. So being careful, we should differentiate the outside function, which is log of x, get 1 over x, evaluated the inside, which is 1 plus x, and then the chain rule says multiply by the derivative of what's inside, and the derivative of 1 plus x is just 1. And for the purposes of subsequent differentiation, now multiplying by 1 makes no difference. I have divided by 1 plus x once, so that's 1 plus x to the power of minus 1. And then if I evaluate this at x equals 0, I just get 1 to the power of minus 1, which is also 1. But now I'm going to differentiate this to get my second derivative, rather than kind of doing a quotient rule with that, which would be a bit daft. So my second derivative, so the outside function here is x to the power of minus 1. The derivative of x to the minus 1 is minus 1 x to the minus 2. Evaluate the inside, I get 1 plus x. And then I guess I will multiply by the derivative of what's inside, but it's just 1, so it doesn't actually make any difference. I will tidy that up slightly, so I get minus 1 plus x to the minus 2. And if I was to evaluate that at x equal to 0, I would get minus 1 to the minus 2. Well, however way you shake it, you get minus 1. And there's just one more derivative to calculate, the third derivative. So now I'm differentiating the thing I just calculated. I'm going to fix the minus, maybe just to make this clear, I'll just say fix the minus 1, and now I'm going to go off and differentiate 1 plus x to the power of minus 2. So that's me fixing the minus. So anyway, fix the minus 1, and now the outside function is x to the minus 2. The derivative of x to the minus 2 is minus 2 times x to the minus 3. Evaluate the inside, which is 1 plus x, times the derivative of what's inside, which again is actually just 1, which makes no odds. So I got minus 1 by minus 2. I'm looking at plus 2, 1 plus x to the minus 3. And if you were to evaluate that at x equal to 0, you'd end up with 2 times 1, which is 2. So now I'm going to use the formula up the top. So y of x, which is log of x, log of 1 plus x, is approximately y of 0, which is 0, plus the derivative at 0, which is 1, times x, plus the second derivative at 0, which was minus 1, divided by 2 times x squared, plus finally the second derivative at 0, which is 2 over 6 times x cubed. And if I just tidy that up a little bit, I get a nice presentation of my answer. Log of 1 plus x, 0 is 0, does nothing. 1 times x is x, and I get minus a half. So adding a negative is subtracting. Minus a half x squared, and 2 over 6 is a third, plus 1/3 x cubed. Okay, very good. So now it says use this to approximate log of 1 plus 0.01. In other words, put x equal to 0.1 into this. So we're talking log of, what was it, 1.01? 1.1. So 1.1 is equal to log of 1 plus 0.1. And we're going to put 0.1 into the right hand side here. So this is approximately x, which is 0.1, minus a half x squared plus a third x cubed. 0.1, 0.1, pause for the calculator. So the calculator says 5 significant, or the question says 5 significant figures. And the calculator does give 0.095 and then 3 recurring. 1, 2, 3. Okay. And then given that correct to 5 significant figures, I have that. Find the percentage error. So the percentage error in any approximation is the error in the approximation over the exact, which I might call Q0. So in this case, we're talking about the difference. So you can, for the error, what you can do is you can do the absolute value of the maybe exact minus approximation. So the exact is in the question above there, 0.95310 minus the approximation, which is 0.09533. We can see there's a small difference here, all right, divided by the exact figure, which is correct to 5 significant figures in the question, this one. And we'll pause to get this out of the calculator. And it is truly tiny. I think I'm going to have to multiply by 100 just to even really see it. It's tiny. 0.0000, and it only wants to one significant figure. That, and if you multiply that by 100%, you'll get it's absolutely tiny. So it's very, very accurate at that value of x. Okay, another question here. The three-term Taylor method has a similar error profile to Heinz method. This is true. What is the disadvantage of using the three-term Taylor method? We may have already seen this. The answer simply is that the three-term Taylor method requires a second derivative. So in that case, I'm going to say it requires differentiation on behalf of the user, and maybe as a remark, and in fact, implicit differentiation if the derivative depends on y. Depends explicitly on y. If you just had a implicit differentiation, that'd be okay. So the four-term Taylor method basically uses the first four terms of would be the Taylor series, I guess. The first two terms is Euler's method, uses a tangent line. First three terms use a tangent parabola, and a parabola, we might just remark, means x squared. It's a quadratic, and the next one up from a quadratic is a cubic. Now quad is funny because normally it means 4, by the way, but the idea is x squared, x by x. That's where the quad comes from. It's a bit weird. And then you have to use quartic for degree 4, but this is using x cubed, which is cubic. So the answer here, the expression on the right side, it's a tangent. It's the best possible approximation to the exact solution that is a cubic. So tangent is kind of covering best. Can I see this? Well, I can't really fit it there. Tangent means it's the best approximation, and cubic means it's degree. There's an x cubed there, basically. So the first comment here is that if you have a second order ordinary differential equation, you have to write it as two first orders. Now here it's nice you've been prompted, but in say your VBA assignment or in what's coming, you may not be prompted to do this. If you try and attempt one of these questions with a second derivative, an ordinary second derivative, and you don't write as two first orders, you're probably looking at 0 marks. You have to do this. So the way you do it is you introduce a new variable. You let the first derivative be a new variable. Now in this particular context of m being the bending moment, the derivative does mean something. It's what's called the shear force. Sometimes the derivative doesn't really mean anything. It would, of course, if say you had x of t, displacement in terms of time, the first derivative would be the velocity. But you can always use v if you want, or some other symbol if you want. Now, the next thing, like I can write down the answer here, right? And if you get the answer, that's fine. So the answer is dm dx is v, and dv dx is minus 10 e to the minus x squared. And it is asking for initial value problems, so you need to put the initial values there as well. M of 0 is 0, and then v of 0 is unknown. Now, how do you get to that second one? To me, you have to A, introduce the first derivative, call it something, and then differentiate both sides appropriately. So if I differentiate both sides here, if I differentiate the first derivative of m, I get the second derivative. And if I differentiate v, I get dv dx. And of course, from what I just wrote, this is dv dx. So that's the first bit. And without that, you're going nowhere. And be aware, you could be given a similar question, but with no such prompt. Okay, now we've got a question here. Using step size of 1.5, and we're going from 0 to 6, use the Euler shooting point method to approximate this. So there's actually a lot of calculations in this. Okay, so we're going to get cracking. Okay, so maybe just before we go, we'll just kind of say roughly what's going on here. So we got m versus x, and we've got a point x equals 0, m equals 0, that's in the question. And then over at 6 here, it also equals 0. So my idea would be to pick a first value v. You can do whatever you want. You can do 0 and 1, but here I want it to make sense. I'm going to try v0 is equal to 0. This is just an attempt. Okay, so you have two differential equations, so two Euler methods, and I'm going to try. So try, and here we'll call it VA. That's our first skill, 0. Okay. Now I actually don't have a calculator with me, so what's going to happen is I'm going to be writing down something kind of from Excel, and because I'm only going to write down 5 significant figures, but Excel might be using more, so if you do the same questions, you might get slightly different numbers. If you're concerned, send me a photo of your work, and I'll have a look. That's, of course, if I'm not on maternity. Now, I think people are having some bit of difficulty with keeping track of things. So, like the first thing is the initial values. So people are writing down, some people are doing daft stuff like, oh, m0 is equal to, say, the first m0 plus step size times the first v, which is 0. And this is absolute rubbish, because m of 0, which would be the initial m, is equal to 0 and nothing else. So this here thing I scribbled out, that's nonsense. We might just do something to help you keep track. So if you were to set up a table, which is not completely necessary here, so you have x, m, and v, and here we're going from 0 to 6 in steps of 1.5, so 0, 1.5, 3, 4.5, and you need to go to 6 here. Now m, the initial m and the initial v are known. Well, the initial v isn't, but we're going to guess the initial v here to be 0. And the initial m is 0, so this is 0, this is 0. So if this is your setup, this is M1, this is V1, this is M2, this is V2, this is M3, this is V3, and this is M4. And actually, this one is in this context, and you don't actually need it. So this is the proper thing. So when you use the Euler method, the initial values are known. You only do Euler method for the subsequent ones. So all of these are done with Euler's method. Okay, so off we go. So M1, the next M1, or the next bending moment, is the previous bending moment, which is 0, plus the step size, which is 1.5, times the previous slope. The slope of M, here you go, this is slope of M, and this is slope of V. Slope M, slope M, slope V. The slope of M is V, and the previous V here for us is 0. So yeah, that's 0. V1 is equal to the previous V, which we're guessing is 0, plus 1.5 times the previous slope. Now the slope of V is dV dx. So here you're getting minus 10 E. Now it must be the previous slope, so it must be the previous x. So at the moment we're looking at this, but the previous x is 0. So that's minus 0 squared. And here we are getting minus 15. Okay, so that's at 1.5. Now let's go to the next stage. M2 is the previous M, which is 0, plus 1.5 times the slope of M, which is V, and the previous V is minus 15. And what pops out here is minus 22.5. And we go again. V2 is the previous V, which is minus 15, plus the step size, which is 1.5, times the previous slope. So that's minus 10 e to the minus x squared, but the previous x is 1.5, so we get 1.5 squared. And this is probably the first one where this is, I'll just put in what I have here, 16.581. I have no idea. Well, there's obviously rounding error because the exponential has an infinite decimal expansion. Anyway, M3 is the previous M, which is minus 22.5, plus the step size, which is 1.5, times the previous slope. The slope of M is V, and the previous V. So maybe, is this clear? Okay, the previous V is minus 16.581, and what pops out here is minus 47.372. We're trying to hit 0, so this is bad as such. V3 is the previous V, which is minus 16.581, plus the step size, which is 1.5, and then the slope of V minus 10 e to the, now V3 you'll notice is at x equal to 4.5, so the previous slope should use the previous x of 3. And what's happening with these negative exponentials is they're very, very small, so we're not getting much difference here. In fact, I get just 583. And then we're trying to hit 0, but we're miles away from it and decreasing, but that's okay. M4 is the previous M minus 47.581 plus step size 1.5 times slope of M, which is V, minus 16.583. And this is coming out for myself as minus 72.246. And this is my first shot, so this is my YA. Okay, now we're going to try, that's a horrendous undershot, so I'm going to try a bigger slope. Now, it doesn't really matter, and you don't have to get an overshot. I'm just going to try 10. So now I'm going to try VB equal to 10. It's my second go. So everything else is pretty much the same except for that. So off we go, we shoot us, and I suppose we want to go reasonably fast. So M1, the previous M, back to the initial M is 0, plus 1.5 times the slope of M is V, I get 10. And here I'm getting 15. Okay, V1 is the previous V, now I've taken it to be 10. plus the step size is 1.5 minus 10 e to the minus x squared. This is at 1.5, the previous x is 0. So here I'm getting minus 5. Next time, m2 is previous m, which is 15, plus step size, which is 1.5, times slope of m, which is v. Previous v is minus 5, and I'm getting 7.5. v2, next v, previous v, minus 5, plus step size 1.5, minus 10, e to the minus 1.5 squared. And this is approximately minus 6.58099. So it actually rounds up to 5810. M3 is equal to previous m plus step size times slope of m, which is v, minus 6.5810. This gives me minus, so unfortunately it's another undershot, 37148, which means 15. V3, previous v, minus 6.5810 plus step size minus 10 e to the minus. Now the previous x, we're at 4.5, the previous x is 3. E to the minus 9 is very, very small, so we're going to see very, very little difference here. I'm getting minus 6.5828. Okay, so be it. And then final M4, we're trying to get 0, we're failing, is minus 2.3715 plus step size times previous slope, which is previous v, minus 6.5828. We're trying to get 0, and we get minus 12.246. And now this is now our YB. So I have my, let's get them together. VA is 0. YA was an undershot. Then I tried a bigger slope of 10, but I got another undershot. And now I need to go and get a formula to calculate what the correct V of 0. And I think that's what the question is it? Yeah, to find the correct V that does the job. So we'll pause and go off and get that. So now we use this formula here. So the V0 is the VA is 0 plus y of xf is the final y value, what we're trying to hit, and that's in the question. You're trying to hit this m of 6 equals 0. You're trying to hit 0. Our first shot was minus 72.246 divided by our second shot, which was minus 12.246, minus our first shot, minus 72.246, minus the difference between the slopes, 10 minus 0. Bang that into the calculator, and you will get 12.041. And then that was part B. Let's read it. Using step size, use the shooting point to approximate m dashed of 0. Yeah, so m dashed being v of 0. Now, hence approximate for 1.5, 3, and 4.5. So there's another 5 marks for doing a third and final shot. So off we go. Let's go. So m1 is the previous m plus step size times previous slope. Now we're going to use that 12.01. And now this is the values we get for mv. Well, we're only really interested in m, I guess, but we need v as an auxiliary calculation. Well, they're going to have errors. I mean, our delta x here, our step size is 1.5, it's very big, but it will get very close to hitting 0, as we'll see. So this comes out to 18.062. V1, previous V now is 12.041. The question did say, by the way, that all calculations to be done to 5 significant figures. Here I get well, as far as I know, this is equals minus 2.959. So that's, well, we'll present our answer at the end. M2, so this is at x equal to 3, is the previous M 18.062 plus step size, which is 1.5 times previous V minus 2.959, and I'm getting 13.623. V2 is the previous V, which is minus 2.959 plus step size 1.5 times minus 10 e to the minus 1.5 squared, and I'm getting out minus 4.5399, which rounds up to minus 4.54, 4.5400. Then the next one, you could make a straight line for me, wouldn't you? M3 is equal to previous M, 13.623 plus step size 1.5 times previous V minus 4.54. Don't have to put in zeros. I get 6.8130. 6.8130. Obviously, you've got the calculator. It's going to take a bit more time. Now, you can check your answer here, because this should, if you continue it, get close to hitting 0. So to check, you could do V3 is the previous V, which is minus 4.54, plus step size 1.5 minus 10 e to the minus 3 squared. And this is coming out to be pretty much the same number, minus 4.5418. And then this next thing should come out close to 0. You got rounding error, which is kind of going against you. So it's the previous M, which is 6.813, plus step size, which is 1.5 times previous V minus 4.5418. And the Excel is kind of giving me very, very close to 0, really. I get 3 zeros, 258. But that's just a check. So if that's close to 0, you know you've gone well. So the step size was 1.5. So we're starting at x equals 0. So this is your approximation to m of 1.5 that was asked for. Your approximation to m of 3 that was asked for. And finally your approximation to m of 4.5. So that's a fairly long question. One of the longer questions on the paper. You will almost certainly get a shooting method. So this is a theory question, naturally enough. So it's asking about finite differences, so I'm just going to bring that formula to us. So this is the relevant finite differences. Now you've got this square meshed tin plate, so you got a plate, you know, but all you have to do, and like in theory, like this can have many very fine mesh, but all you're focusing on actually is just something like this. So a temperature at a certain point, you're going to want to show that if you approximate the Laplace equation using the finite differences below, you get that the temperature here is the average of the 4 adjacents. So we're just going to take that little bit out. So what you're looking at, and you want to set yourself up. Don't be worried about the funny notation. I mean, to me, what would be perfect here is something like this. Like, don't be worried about TIJs. So this is the x-axis. This is the y-axis. This can be your temperature. And you could call this temperature right, temperature to the left, temperature up, and temperature down. And it doesn't really, you know, this is all you really want. And then this thing here, so the I+1 means next. XI means current, like that's where we are, current. And then this is previous. And then to kind of understand what this is, so this is the next with respect to the y variable. So from T is where you are. I guess this is the current. T up, looks like T4. T up is the next in terms of the Y. So if you go up to the next Y coordinate, that's the temperature. And this is the previous with respect to Y. This is the, and then if you go, if the temperature in the middle there is your current temperature, and you go to the next X coordinate, that's going over to where TR is. So this is the next with respect to X, and this one is the previous with respect to X. And all we have to do is approximate those two second derivatives using this finite difference thing down below. So we have to approximate these two using this. So let's write something like the sum of the two partial second derivatives equal to 0. I guess what we're saying is approximately, this implies we get an approximate equation. So using the thing just above on the X, so what's the next X? I would say that is TR. Minus twice the current temperature is just as T in the middle. And then the previous with respect to X is TL. So plus TL, all divided by delta X squared. Now do the same for the Y direction. So the second derivative, the partial derivative temperature with respect to Y. And remember, of course, the partial derivative is important. It means that the X coordinate doesn't change. And as you go along the Y axis, the X coordinate doesn't change. That's why I like the diagonal things don't come into it. So the next one in terms of Y is temperature up minus twice the current temperature is T, and then the previous with respect to Y is temperature down divided by delta Y squared. But if you have a square meshed plate where this is delta Y and this is delta X, if it's square meshed, they're actually equal. So you can multiply both sides. So multiply both sides by delta X, and note that delta Y is equal to delta X. And actually, I suppose we're multiplying both sides by delta X squared. So if you're multiplying both sides by delta X squared, now if you're multiplying a sum, both of them are going to get multiplied by delta X squared. So the first term multiplied by delta X squared, the multiplication gets rid of the division. Now multiply the second term. Now delta X multiplying by delta X squared doesn't get rid of division by delta Y squared, except it does because they're equal. So multiplying by delta X squared is the same as multiplying by delta Y squared. So that'll get rid of division by delta Y. And 0 by delta X squared is 0. And all you have to do here is just add the 4t to both sides, because you've got minus 2t minus 2t. And then swap sides. I mean, A equal to B, B equal to A. So I have 4t is equal to the right temperature plus the left temperature plus the up temperature plus the down temperature. And then to finish off, I divide both sides by 4. So the temperature at any point approximately is equal to the mean average of the 4 adjacent temperatures, and those adjacent temperatures are found to the right, to the left, up and down. That's that. Okay, another question here. The finite difference in question, to approximate these first derivatives, you could come up with kind of somehow reasonable answers by like saying using those two for the X and those two for the Y, but you can actually do better because you can take account of the 62 and the 36 and the 71 and the 40 to get a better one, and that's what we're going to do here. So let's bring in that finite difference. It's called the central finite difference. It's basically going to do next minus previous divided by the distance, and the distance here would be delta X, and 2 delta X, excuse me. Okay, here we are. So yeah, so we're going to approximate these partial derivatives using this thing here. So it's so this would be next, and now the genuine previous, it's not the current because it goes back to I minus 1, but if you do that, the width is 2 delta x rather than 1 delta x. Now maybe I'll just kind of show where this is coming from a little bit. So it's like you got this temperature, this temperature, this temperature. It doesn't quite show up in this picture over here. And so say you got this could be the next temperature, could we maybe call it Tn, not a great idea. Current and previous, and the distance between these are both delta x. And so if you do next minus previous, so that's a change in y, but the change in x is 2 delta x. Okay, so let's approximate these partial derivatives. So the partial derivative with respect to x, so here we're talking, this is the x and this is the y, so we're looking at these two for the x. So we're calculating this vector at this point, the point in question in the middle. So the next to the 52 is the 62, the previous to the 52 is the 36, and the delta x, well, let's just write 2 delta x for now. Well, we won't, because we know delta x is 0.2. And we'll get that with the calculator in a minute. And we also have to do the partial derivative in the y direction. So the next temperature in the y is 71, and the previous temperature in the y is 40. So the number pops out for this one to be like 65. And the number pops out for this one to be minus 77.5. Now, it doesn't mean so much at the moment, but we have this heat flux density vector then is minus k. Now, the minus is what ensures that this vector, this flow of heat, goes from hot to cold. So minus 0.241 times these partial derivatives, which are, so it's plus 60, plus 77.5, 65, 77.5, and so we're talking minus 15.665 and minus 18.678. And if you want, you could write these in terms of i's and j's, minus 15.665i minus 18.678j. And if we draw it, it should make some sense. So it's approximately equal along the x and the y, but going left in terms of x and down in terms of y. It's more slightly down, so kind of under the 45 degrees, so maybe something like this. And here you can see kind of easily enough, yes, it is going from hot to cold, or what have you. So this next question is fairly well covered in the heat equation. If you need to, I suppose the lectures more so, lecture videos, but also the worked exercises, if you want to go down to those. So I'll do this one fairly quickly. It's on page 174. So the first is to write the heat equation in this particular form here. So we're going to use, if we got some finite differences around, we're going to use this finite difference here, this one, and do we have another one? Don't think we do. No. So we have we'll just write down the actual form. So we're going to be using this, that a second derivative can be approximated like this with next, current, and previous. We're going to use this to approximate this second derivative here. And then the other one is going to be that a first derivative, dy dx, at a point xi is approximately y of xi plus 1. So that means next minus current all over delta x. Okay. So I think for this one, there's nothing more we actually need. Well, we need another setup. So I'm going to take those two finite differences as read. So the thing we're working on is, so these are 3 temperatures along the rod. Say temperature I minus 1, temperature I, and temperature I plus 1. They're all at the same time L, because here we've got distance changing and time. And then temperature I the next time is temperature I, L plus 1 means next time. So here I think our answer is going to be in terms of K. So we're talking about K times second derivative with respect to X equal to first derivative with respect to time, and then approximately this gives us. Okay, so that second derivative above, let's write in some stuff here. So this, now this is the x-axis here. So you just draw this. This is the x-axis, and this is the time axis. So this is next with respect to x. In all cases, this is the current. And this is the previous with respect to x. Previous with respect to x. And then this is the next with respect to time. Okay. So this second derivative, so we're using, where is it? This yoke here. Next minus twice current plus previous over delta x squared. So this second derivative, it was next in terms of x, ti plus 1l, minus twice the current, twice til, plus previous ti minus 1l, divided by delta x squared. And I don't think we know what delta x is here. Let's just check. No, it doesn't say anything. And then the other partial derivative, we're using this thing over here. So this is next minus current over delta x. And we're doing this in the time direction. So the next temperature is TIL plus 1 minus the current is TIL. And here we're not dividing by delta x because it's time that's changing. We're dividing by delta t. And our job is to solve this little equation for this to find temperature I at the next time in terms of some previous temperatures. So this isn't too difficult. From here, I'm going to multiply both sides by delta t. And of course, we're calling that A is equal to B, then B is equal to A. So the right-hand side is going to be my new left-hand side. And when I multiply both sides by delta t, it'll get rid of the division by delta t. So I have t I L plus 1 minus t I L equal to. Now I'm going to have k, and now I've multiplied by delta t, and I'm going to pull out the delta x squared. And this little yoke here, we're going to define this to be equal to, sorry, the wrong way around. I'm going to define this to be lambda. And then we get the next temperature over minus twice the current temperature plus, when I said temperature over, yeah, to the right, and then the temperature to the left. And then all that we have to do here to answer the question as asked is to add, I guess, the previous Ti to both sides. So we end up with the next Ti is the previous Ti in terms of time equals plus lambda, which we've just defined to be this k delta t over delta x squared, times the temperature to the right at the previous time minus twice the previous Ti plus the temperature to the left the previous time. Okay. Our next thing then is to, I think, give the value of lambda. Well, it says give a condition on lambda that guarantees that the approximations are what are called stable with good transient. This is simply a theory question, and it's very, very simple. That lambda must be kept less than or equal to a quarter to get that. Then it says as time goes to infinity, sorry, there's question B. Give a condition on lambda that guarantees that using that to approximate solutions of the actual partial differential equations are stable. In other words, if time goes on, you get close to a steady state, and good transient, that the calculations that you do in the meantime are good approximations to the transient temperatures that are the temperatures as it goes from the initial temperature to larger. Part C, as time tends to infinity, the rod approaches steady state, where the temperature at each point tends to a constant. So then explain why the steady state satisfies this. So if the temperatures go to constants. That is to say that the derivative with respect to time, like you can look at the derivative with respect to time to find out if something is constant. If the derivative with respect to time is not 0, then it's changing. But if it's constant, it's not changing. The rate of change of it is 0. So we get partial temperature, partial time equal to 0. And then if you look at the heat equation, in other words, this thing, if the right hand side is 0, then the left hand side is 0. So we're getting that in steady state, this spatial second derivative is 0. I think that's what we were asked, was it? Yeah. Hence, explain why the graph is a straight line. So this is the steady state. Well, this is very easy. If you can divide both sides here by k, maybe we'll leave this to the next part. Is this part D? No, this is part I. That's freezing on me. This is part I, and this is part II. So you can divide both sides by k there, and you'll get that the second derivative, and I guess it's saying that if time, like the temperatures depend on distance and time, and if time has gone to infinity and temperatures aren't changing in time, the temperatures just depend on distance. So this is why the partial derivatives become ordinary derivatives. And then the question is, what function has a second derivative of 0? Now you can actually anti-differentiate both sides twice, and you will find that steady state temperature is equal to mx plus c. Let's read the question there. Explain why it's a straight line as, so it's a straight line. In other words, steady state straight line as only straight line. Straight line has 0 second derivative. That's what I would have been looking for there. Okay, on to the final question. So more examples like this done in the heat equation video, or both lectures and the exercises. So we'll go reasonably quick here. So we have a 0.8, we might do a bit of A here just while we have the question in front of us. So we have a 0.8 meter rod, and we're asked to mesh it into 4 equal pieces. So the actual x points are, well, they'll be important at the end. So this is x equal to 0, and this is 0.8. Chop that into 4, you're talking 0.2, 0.4, 0.6. And then in terms of temperatures, at the left, at x equals 0, we have 30, and then 90 at the other end. So this is 30 and 90, and we will call this temperature 1, temperature 2, temperature 3. So that's meshed into 4 equal pieces, and we might just write down here while we're here that delta x is 0.2. And using delta t to be 0.1 and the equation derived previously, so we will be using this thing that we derived to approximate the temperature at subsequent times. So maybe we could write down like maybe something here that it says that at time equal to 0, the temperatures on the rod, so the distance is between 0 and 0.8, so on the rod, those initial temperatures are 0. So that looks like temperature 1 initial is 0, temperature 2 initial is 0, and temperature 3 initial is 0. Now they're not guesses, that is the actual at time equal to 0. So that's what those bits mean. So at time equal to 0. And now they're going to heat up, and they're going to heat up using the formula that we had above. Now we might just calculate our lambda here. So our lambda was k delta t divided by delta x squared. So our k is 0.08, our delta t is given to us there as 0.1, and our delta x squared is 0.2 squared, and we'll go into the calculator to find that. And I am finding 0.2, which is less than a quarter, so we're good to go. Okay, so let's go. So temperature 1, this is using this formula above, kind of, so I've gone over the shop. I'm using this thing down here. Maybe I'll try and pick it up. This could go badly wrong. Oh, copy. Hopefully this will work now for me. Paste. Hi-oh. Right. So, okay, so T11. So notice the L's are the previous in time. So the previous T1 was 0. Lambda is 0.2. And the I plus means the one temperature to the right, which is temperature 2. And the previous temperature 2 is 0. Minus twice the previous temperature 1, which is 0. And the Ti minus 1 is temperature to the left. And to the left of temperature 1, we have the heat source at 30. Now I'll put all these in and then we'll go to the calculator at the end. T2 at the next time. So we're going to time 0.2. So we're going to do 2 of these iterations. The previous T2 is 0 plus lambda. The temperature to the right of temperature 2 is temperature 3, which was previously 0. The previous temperature 2 was previously 0, and the temperature to the left of temperature 2 is temperature 1, which is also 0. And that one I can do without a calculator, 0. And actually I can do this one as well, because 0.2 just as a fifth. Excuse me. And then T31, previous T3 is 0 plus lambda. The temperature to the right is that heat source of 90 minus twice the previous temperature 3, which is 0, and the temperature to the left of temperature 3 was temperature 2, which is also was 0. And a fifth of 90 is 18. So this is time equal to 0.1, and the question is to go to time 0.2. So that's temperature 1 at the second time, 2 time steps. The delta T here was 0.1. Previous temperature 1 is 6 plus 0.2. Temperature to the right was T2. The previous T2 is 0 minus twice the previous T1, which is 6, plus the previous temperature to the left, and to the left was this 30. We'll ask the calculator for that soon. T2 at this time is the previous T2, which is 0 plus 0.2. Temperature to the right previously was 18, minus twice the previous is 0, plus the temperature to the left, which is 6. We'll ask the calculator for that in a moment. And then T3, previous T3 is 18, plus 0.2. Temperature to the right of T3 was the heat source 90, minus twice the previous temperature 3 was 18, plus the previous temperature 2, which is 0. We'll pause for the calculator. So calculator says that this is 13.6, this is 4.8, and this comes out to be 12.8, which is slightly unbelievable. But the reason this happens, and actually that's wrong, let's pause. So my apologies, it should be 9.6. The 4.8 is good, and 28.8. Okay, right. Part C, find what happens when time goes to infinity. So again, more in the heat equation ones, if you want to see in more detail, slightly slower. So as time goes to infinity, I think we showed in the previous question that the steady state temperature is a straight line. And here this was a rod of length of 0.8. The temperature on the left was 30, and on the left was 90, and it goes from 30 to 90, and the steady state temperature, which is the same as the limit as time goes to infinity, the temperature as a function of x and t, it goes to a straight line. And we can find the slope here because the rise, it goes from 30 to 90 is 60, and the run is 0.8, and we can calculate that. It is 75, and then we can just do y is equal to mx plus c. So the steady state temperature, mx plus c is where it cuts. That's that question. And then the final thing, suppose that you had to keep on going. So what happens, and if you do lab 8, or if you did lab 8, you'll learn this, that the temperatures increase from 0 up towards that steady state. Now you're looking at temperature at 0.2, 0.4, and 0.6. If you put those x values into that steady state formula, I believe you will get 45, 60, and 75. And what you want to do is you want to keep on running until temperature 1 gets close to 45, temperature 2 gets close to 60, and temperature 3 gets close to 75. So the stopping rule would be until the absolute value of temperature 1 minus 45. Now what's appropriate is less than 0.5. If you kind of push that to 0.1, it takes ages to run. So this is kind of appropriate. And you also want the distance between temperature 2 and 60 to be small, and the distance between temperature 3 and 75 to be small. And that is a wrap.